thank you all for joining us today for our July session of Passion Behind Design. For those of you that are new to these sessions, Walter P. Moore is an international engineering firm specializing in structural engineering, forensics, and infrastructure projects. Projects we work on are sports, aviation, healthcare, office, and educational facilities. Today we have Kat Chan, who works in our building enclosures group, who will be sharing with you about her experience and how she entered into this career. If you have questions during the presentation, please type them into the chat. And with that, I will hand it over to Kat.
Great. Thank you so much, Annie. So today's presentation, as Annie mentioned, is going to touch upon how I got into facades, and then I'm going to highlight one project that's close to completion. It's a project very near and dear to my heart, so I'm really excited to get started. So by way of introduction, I thought I would give some background on how I came into working as a facade engineer. So I graduated from Columbia about 9 years ago, and I've experienced working in the New York industry and area for 9 years. I graduated with a degree in structural engineering from the Fu Foundation School of Engineering and Applied Sciences. But I always knew I really appreciated architecture and I really wanted to work in a collaborative space. So after working at a couple of other firms, I joined Walter P. Moore at 2.5 years ago, and I am a senior technical designer and associate. During the entire time, I worked comfortably in the facades discipline that has multiple different facets, touches different disciplines, and we'll get into that later. An additional part of my role at Walter P. Moore is a council member on the Diversity, Equity, and Inclusion Council. This council looks at how we, as design professionals at Walter P. Moore, the industry and beyond, can look at social equity and think about how we can change the world and the industry we work in. So a little bit of exciting, fun photographs is I actually don't have a very good photograph of myself from when I graduated, but I do have a photograph of me climbing a statue over there on the upper right-hand corner. Very illegal, don't do it. Then there's a photograph here on the bottom of my team. So the Enclosures Engineering group at Walter P. Moore is bi-coastal. We have offices in LA and New York and a couple of other folks scattered around the country. And that photograph is from our summit about 2 or 3 years ago, and it was the first time we got to be in the same place together. So to me, that was a really cool photograph because I got to meet the folks finally that I've been working with. Now, a little bit outside of what I do at Walter P. Moore. I'm also a member of the Society of Facade Engineers. The society is an international group that ties together folks who are like-minded in the facade engineering groups around the world. So it could be folks in academia, it could be folks who are like me, working in industry, or folks who are in the construction industry. In addition to that, I'm an adjunct professor at Columbia University in their architecture school. So I teach primarily about enclosures, but I also emphasize on the collaborative nature of what it means to be a built environment professional. In addition to that, I'm also a planning committee member for the Future of Design Symposium, which is a symposium that brings together professionals to think about how we can collaborate with each other and push different frontiers, whether that means different technologies, different ways of working. Most of the time, it's pretty open-ended, but it's a really great way for folks who might be interested in the built environment to dip their toes in to see what we talk about when we're not working together specifically on projects. And lastly, I wanted to plug the Design Advocates, which is a design collaborative that focuses on pro bono work by designers, architects, and engineers to give back to the communities affected most. It was performed around April 2020 during the pandemic. So this specific organization is quite near and dear to my heart. So I wanted to give a little introduction of what I do at Walter P. Moore and outside. And here is a map of the projects I've done since I started working. I've kept this map up in Google throughout the years, and to me it's quite important because each of those little teal dots indicates a project I've worked on in some way, shape, or form. And part of being a facade engineer, consulting engineer, allows me to work around the world, even if I myself have lived in New York. So you see each of these little dots kind of indicate a different project. And to me, over the years, as I do update this map once every few months, it's exciting to see that more and more dots pop up. And I wanted to touch upon a couple of projects in addition to the big one I'm going to talk about later. So the top two are projects that I'm working on currently at Walter P. Moore. The one in the upper left-hand corner is a university building that has a pretty cool color-changing iridescent facade. So not only is the material pretty exciting, the way in which the project was put together. It was quite cool. That was part of the problem statement, you could say. And then the upper right-hand corner is a performing arts center. That's different materials that utilizes a lot of like formed metal panel, a lot of geometry going on there. Both projects are with architects in New York City, but are in Florida, respectively, and Omaha. So it's really cool to be able to work in New York, but work with architects local to the different areas that your projects are going to be in. The bottom three are projects I worked on in my previous place of employment, which includes the Dubai Sustainability Pavilion for the World Expo. That's the left-hand corner. The one in the middle is the Shanghai Jewel Airport that has a waterfall in the middle. It's the world's largest steel dome that's topped with glass. And then all the way there on the bottom right is a renovation of a historical space here in New York City called Tammany Hall. And the hall itself was part of a political group that has since been restored and now is a commercial and mixed use space. It's got a new glass ceiling on top of it. And I just wanted to bring up each of these have their own stories and are really integral to the communities that they're built in. And to kind of tie it all together, these stories and these experiences I've only been able to have because of facade engineering. So, first question. Why is facade engineering needed? So this question, I think, is something I get pretty often, especially because I myself didn't know what facade engineering was until I graduated. So what is facade engineering? I think is where we should start. And it's essentially the discipline of leveraging different materials and their performance to protect the building. So if a building is a person, the facade is the skin. If a box is a parcel, the facade is the envelope that surrounds it. And so by making sure that the facade works well, you're protecting the structure that's inside, you're keeping the people warm or cold, depending on what it is they want to have in that. And you're protecting not only the people in the building, but also the building systems, whatever the use of the building is, protected from the elements.
So Kat, we have a question before you move on to the next section about the projects that you have worked on in relation to the map that you showed. Have you visited every project that you've worked on?
Almost. The one in Dubai and the one in Singapore, which are the two that quite near and dear to my heart, I have not made it to. It was part of my plan to sometime during last year, but the pandemic had other plans. So hopefully in the next 5 years, I will go and see it. Otherwise, I've seen almost every project.
Okay. And do you have a favorite place that you've visited?
Oh, that one's hard. I can't say. I think every spot has been like uniquely its own. I think the most fulfilling visit I've had would actually have to be the Carnegie Mellon Tepper School in Pittsburgh. It was one of my first projects that I completed completely remotely, but I was the facade lead on it. So that was really fulfilling to like get on a plane and like see it come through the earth. It was really cool.
Nice. All right, let's hear more.
Awesome. So now I'm gonna dive into the project that is most recent to me. And the image that you see here is a rendering, which means it's an architect's image of what they hope the building will look like. And this building is the ThyssenKrupp Elevator Headquarters building. It's part of a campus that the tower itself is the Innovation, Qualification, and Classification Center. It's essentially a test center for elevators. So ThyssenKrupp is a German company that designs and innovates the way in which we move through buildings. So whether that be escalators or elevators, they're the folks to look at. And so they've got elevator towers from around the world, but for this specific project, that we'll be talking about today is a project outside of Atlanta in Cobb County. And it's a project that we didn't do by ourselves. Every single project has multiple consultants and a pretty big project team. Even if your project is small, even if it wasn't an elevator tower, For us here, we provided structures, facades, and whole building life cycle assessment. So if you saw Kelly Roberts' presentation previously, she divulged into what that discipline is. And she and her team actually did an analysis for this building of ours. So what's really cool about this project is that the tower is used to test and showcase a new type of elevator technology called the multivator. So traditional elevators have to rely on cables and they can only go in one direction, up and down, and they're pretty clunky. However, with this new technology called the multivator, instead of cables, magnets are used. So now you can change directions. It's like Willy Wonka's chocolate factory level sort of situation. It's really cool because it goes from being like a design, an idea, an image, an animation, and then it becomes like a full scale model where you can see the different angles of the tracks rotating, and then the elevators themselves can move. It's a really cool technology, and it's definitely not something that I ever thought I would work on. So I'm glad that I was able to work on this project, and I was really glad that this technology I know more about now. So whenever those two things come together, I think it's really very exciting. So here I have an example on the left, yet again, an architectural rendering, and then an image of the building and construction on the right. So you can see on the left here, all that blue glass is going to highlight that showcase space. That's where the elevators are going to move up and down, left and right during the nighttime and the daytime. The glass here, as you can see on the right, is really quite, you can kind of see the two come together and how they compare. But also worth noting is the architectural facades on the other three faces, which includes this metal panel, which is really very eye-catching. One of the questions I get often is, what's the most important for facade engineering? And I would say that it's almost a trick question because almost everything is worth considering. And depending on where your project is and what it's trying to do, different concepts, different performance will be required. So if you're in California where there's a lot of earthquakes, your facade is just like your structure is going to have to respond well to earthquakes.
So Kat, quick question. What are the different conditions across the US? So you mentioned California with seismic zones. What are some other areas that have special conditions that need to be considered when you are designing a building?
That's a great question, Annie. So a lot of it is about understanding the weather patterns through the year for your specific project site. And as someone who grew up in the Northeast, I had to learn quite a bit about different climate zones. I was like, wow, places don't have all four seasons and all of them are humid. That's fascinating. One specific example is in Scottsdale, Arizona, I had a project and there was this really beautiful lattice structure at the rooftop. And we had to work with the architect to design it, just like understand how we could do it and why was it a challenge. Turns out dust storms are a thing. And it can be really challenging because beyond having wind load on the lattice itself, all that dust accumulates. So you have to design this facade in such a way so that the dust doesn't accumulate. And if it does, it can be easy to clean off.
Okay, thank you.
Absolutely. And in areas where it's cold, the slide here touches upon some of the more challenging items that we have to think about. And part of the design of facades is to emphasize that the facade is the primary protection against the elements. And so what are the elements? It's nature. And what can never be controlled? Nature. So we do our best. We look at historical data. We look at other projects that are in the conditions, and we kind of see how past projects have succeeded and how they failed. And with the advent of computers and simulation softwares, we've now been able to guesstimate, optimize, on optioneer, different ways in which we can address natural phenomena. So the first one I think would be wind. That's the first thing, is when the wind blows and it's really, really strong, is your buildings going to stand? Is the facade going to stand? Like, for example, have you ever been in a really bad windstorm? You'll see shingles fly off of buildings, right? So that's what we don't want. We don't want anything to fly off the building. And we also want it to protect people who are inside. So the upper right-hand corner image with the tennis ball is a wind tunnel simulation image. Each of those white lines is basically indicating wind flow going around the tennis ball. Similar image to what you would see in like car commercials to show like how aerodynamic a car is. Same concept for a facade. And the image right below there is a simulation. So it's a computer program that does the same thing. But computer simulations, of course, are just also our best approximations. The lower right-hand corner image is one such example of what's called a wind tunnel test, where a scaled model is built and then the wind is basically pushed through in this tunnel. So it's basically simulated, and there are little dials that can measure the wind that your building is going to have. Now, one item I also want to touch upon, which is not glamorous, but is so important, is also ice and snow accumulation, which is the middle image there. So what happens is when ice and snow accumulate, it can be really heavy, and dainty, really lovely architectural elements are then really at risk because they can fall off because they weren't designed for the ice and snow. Even though ice and snow only affects the upper half of our country in the United States, it's enough to be a cause for concern. So you got to think of like around the year, besides not just summer and sunny days, but also thinking about winter. And finally, rain. So you have to be able to weep out any moisture that comes into your facade so that the water doesn't come into your building. Because if it does, then you have mold risk. You know, if you have a priceless Picasso on the wall, or you've got this like beautiful tapestry and your wall is leaking, it's going to get damaged. And it's things like this that we don't really think about because we've become so accustomed to our conditioned spaces to be really comfortable and for them to be dependable. So I kind of like to think about it as if a building is a person, or a building is, let's say, an animal of any of these ones that we see here. And the enclosure basically functions as your first line of defense for like thermal control. Like if I am the rabbit that's in the Arctic on the upper left-hand corner, my fur is the first line of defense. The water that falls on me is going to dry off. It's never going to come into my body and make me cold. And it camouflages me so that I'm safe. For example, also for warmth and insulation, like as a rabbit or as the sheep, that insulation is keeping me warm in the winter climates. And in the summertime, I'm going to shed it and I'm going to be temperate. So it's these adaptations that animals and organisms in nature have been able to evolve from. But buildings, as much as the analogy can falter, can't change through time. So we have to think about how we can best equip the building, in the facade's perspective at least, to work with the rest of the building systems throughout the year and to keep the building and the people inside safe. So I'm going to, with all of that as the lens of for this project for the TKE Tower, I'm going to walk us through what's my day-to-day look like when I was designing the project. So one of the first things to note is we worked on this project with an architectural company, an architectural firm called Gensler, and the aesthetic was something that they knew very early on that they wanted. So the aesthetic is usually a word that means the design intent. What do they want to see? What's the texture? What's the color? What's the material? And so the image in the middle there is this kind of like shimmery metal panel, and that's something they knew they wanted to incorporate into their building. And so that constitutes as wall type 1, which is that hatched or blue area there called tower cladding. It's got all this like panel that's angled outward ever so slightly. And having that panel angled gives you that shimmering effect as you walk around the facade. The red is this glazing that highlights that multi-faceted atrium space that we talked about earlier. And then wall type 3 is the combination of those two. It's this penthouse observation deck, which is really very cool because this tower is also the tallest tower in Cobb County, and it is the tallest also as allowed by code. So it's a pretty cool spectacle, and simply that like now when it's really close to completion, if you stand at the top of the tower, you can see the landscape for miles around. So I'm going to now jump into wall type 1. So that's the blue area there that's highlighted. And I'm going to talk about materials. So part of the really cool thing and what actually attracted me and kept me in facade engineering is the plethora of materials that you can use. So we always knew the architects wanted to have some sort of metal panel, some sort of shimmering effect panel. And so one of the first things that came about was to have a perforated aluminum panel. And perforated panels simply mean aluminum panels with holes in them. And the reason why the holes are cool is that you have this interplay of light. So at the tower, when you have this panel on top of a piece of glass and you turn the light on in the nighttime, it has this glowing effect. And then we also explored other types of perforated panels. So for example, for this project, each of those holes is cut, laser cut, and there's a little davit that touches the coin at a certain angle so that the hole is the coin is basically stuck at an angle. It gives us like really cool shimmering effect. And this one here is another example where like an image is put onto a panel with laser cutters. And so these are all examples of like being creative with just a really basic concept of like cutting a hole into something can have so many different effects. So one thing of note here is that we also thought about what could we do that would be more cost effective. And so this is an example of expanded metal mesh where like the metal mesh is cut into little slots and then it's pulled. So reason why this is more cost effective is that you don't have to make little holes, but it's actually pulled out. And also the idea is you would potentially use less material, less waste, because there's no like coins after the holes. So one question that then after we figured out, okay, these are the materials we can play around with, how do you put the panels on the tower? So we thought a lot about, well, this is a really tall tower. It's 440 feet tall. It's all concrete on 3 sides, so it's going to be really hard to put those up. So I'll get into it in a little bit, but the idea that we came up with is, well, we're not quite sure exactly how they're going to install these panels, but we're going to give it our best guess. And our best guess is that there's going to be some sort of optimization. Optimization means that you're going to put a couple panels together at the same time, or you're going to be strategic about how you approach it so that you can potentially save some time or some cost. Annie, are there any questions or should I keep going?
I think you can keep going.
Great. So here you can see the tower cladding modules that we're playing around with. And you can see here, we were either going to work with spans that are 21 feet or 42 feet. And this is just like an arbitrary, like best guess. Let's see how this is going to look. And so on the left here, you'll see these like rectangles, and those are elevation views. Those are indicative images of how we see these panels from the front. And then on the back elevation, which are images on the right, you see these blue elements, and those are steel elements, essentially, that the panels would be installed on the ground and then lifted up. And we had 2 approaches. One was called the post, the single element, and then the ladder, where it's multiple elements put together. So, and we also realized that about the angling of the panels itself was going to be really hard. So for either approach, we knew we had to be able to address that in some way. So we used brackets. So one such idea would be that the perforated panel, as you can see on the bottom of this image, is going to get attached to a bracket, and then that gets attached to a tube, and then that gets attached back to the structure itself. And the bracket itself is what is going to define that angle for us. So in a way, the only thing that changes per element is this bracket and nothing else. And so this is the idea that we brought together with the architect, and we're like, this seems pretty good. And we talked to other folks who would provide systems like this, and they're like, this seems pretty good. So I am aware that some of you guys and gals, folks, are a part of the ACE mentorship program and would be interested to understand how this falls into the design process. So these diagrammatic images that we see here are what you would call concept level or schematic level. And then what you see here, these drawings are instead what would be called drawings. So these drawings here would be what we produced in design development and construction documents phases. So these are much more detailed, and you can see we really thought about how that bracket is going to look. Right now we have like gusset plates, and you can see all those bolts. And we really thought about what are the dimensions we need for the support frames. So I wanted to bring this up to basically show just like the progression of how you go from like concept of like we have a panel that needs to go onto the tower to putting it into images so that anyone can understand it. The next step would be going towards engaging a contractor. So a contractor or facade system supplier, they go by different terms, are basically folks who are actually going to be getting the material, making what it is that needs to be made for the facade, and then putting it on to the facade itself. And this example here, the producer is a group called Southeastern Architectural Systems. And so they took our concept and were like, okay, we can work with this. And they had what's called a proof of concept. So they sent over a document that showed all the just different angles that they can achieve using their approach that was quite similar to ours. And then ultimately, they have what is called their shop drawings. Shop drawings are really detailed drawings of the system that they are going to be providing. And then we review it with the architect to confirm that, yes, this achieves what we're looking for. And one thing I have to mention per our earlier conversation point about ice and snow accumulation, this came up on this project, even though it was in Georgia, and even though Georgia is known for warm weather, in the wintertime, there is still snow and ice, specifically freezing ice in the wintertime. So why is this a concern? So as you can see in the caution sign in the lower left-hand corner, falling ice can be a challenge to pedestrians in the space. You can see on the repeat image on the right-hand side where there are louvers that become a shelf because the ice gets piled on. And then you can see in the upper right-hand corner this image of a lattice where ice has been accumulating just on posts, just on little tiny elements. And so we were thinking, well, granted, the top right image is from New York City. If there's going to be ice accumulation, there's a potential that that's going to occur as well. So that all being said, as I mentioned, nature cannot be controlled and cannot be fully predicted. Our problem statement essentially was, how do you minimize this challenge? How do you minimize the effect of potential ice accumulation? So I'm going to show this video here, and this is just orienting us to the building itself. And you can see the articulated angles here. And this was a visualization that we had done to show basically the relationship of the different perforations. So we looked at a 1-inch diameter hole versus like a 0.375 diameter hole, and essentially thought to ourselves, okay, what will be the differences? A bigger hole versus a smaller hole. The bigger one will allow more particles through, so there'll be less accumulation, versus the small one will allow less through, and there'll be more accumulation. So with more accumulation, what does that equate to? That means the whole panel is going to be solid, and that's what we don't want. So in order to make sure there's no ice that builds up so much, we went with a larger perforation. And so that's the story there about something that we worked with the architect with and with the supplier to try to figure out how we can best approach something that we can't really control. So one question that came up was, is ice accumulation always a consideration? So not always. So similar to the conversation that we had earlier, when that project in Arizona, ice was not a concern because really there wasn't enough humidity in the winter time for ice to accumulate. So the answer would be no. However, one thing is important to note is I myself was surprised that Georgia would have ice accumulation concerns. So it's always important to keep an open mind and to stay creative about where your project is located, because you'll never know unless you ask the questions to just strike it off the list. And by doing that, it also gives you a much fuller picture of not only the project conditions, but where you're designing as well.
So Kat, how many iterations did you go through, design iterations did you go through with the architect before you decided on this system and this design?
So in terms of the system design itself for the panel, we went through quite a few ones. So even if it wasn't going to be perforated aluminum panel with the circles, we actually went through, I would say like 3 or 4 earlier iterations of different materials. So at one point in time, there was an idea of it being all glass. That was too costly. And then there was an idea of it being a flexible membrane sort of sail, but that got to be challenging from like how would you even design that because of just the spans. And so we eventually landed on some sort of metal panel, which is what you see here. And I think the really cool part of it was we had an active role in how to define the perforations. And so we were able to get the ice and snow accumulation concerns early on. So versus having it be like oh no, an after effect change, because it was allowed to be at the very beginning, we were able to design together. And so that became like a better solution versus having to fix something afterwards.
Great. Thank you.
For sure. And so now I'm going to move over to the glazing. So the glazing here is this multi-story space that has not very few. It's like 4 or 5 floor slabs where there's a main elevator shaft on one portion of it. But for the latter half of this eastern elevation, it's all open. There are no floor slabs in the shaft space itself. So it's really cool because it's just a gigantic atrium. With that in mind, I had never designed a glass enclosure for an elevator shaft at all. So similarly to looking at like what the weather conditions are for a project space I've never worked in, I did some research about what is required for shaftways, and it turns out it has to be laminated glass cladding. And the reason for it is that you can see in these images here that traditional glass, like just annealed glass or tempered glass, breaks into tiny little pieces. And you don't want that in an elevator shaftway because those tiny glass pieces can get stuck in the machinery. And that becomes an additional hazard, which is really very scary. And one thing to know why those two glass types are used is that annealed glass is literally the pane of glass that comes out of the oven. It's a like natural sheet glass and it's quite weak. And if it breaks in these giant shards, and it's really very dangerous because you can cut yourself on it, even just trying to pick it up. Versus tempered glass, it's the same sheet that's put into the oven again to be heated at a higher temperature. And by reheating it and then cooling it, it gets stronger. So that's great. But when it breaks, you have all these tiny little pieces. So big piece or little piece falling into an elevator shaft is just going to equate to some problems with the machinery. So really, it made a lot of sense that the building code required laminated glass. And so knowing that and having that in mind, we were able to design with that in mind really early on. So you can see this image all the way to the right here. This is what laminated glass looks like. It's 2 panes of glass that has a plastic interlayer. Those 3 things are heated together up really, really hot, and kind of like a grilled cheese, they stick together. And basically, the 2 panes of glass, if and when they break, the interlayer is going to hold it together. So that way, even if it kind of gets a little wiggly because it's a piece of plastic, there's no glass pieces falling out or less glass pieces. And that's really important for an elevator because the worst thing that can happen is if there's what's called fallout, like what was a glass pane is now a hole, you have a pretty serious pressure differential, which will affect the way the elevators work. So with this in mind, we thought, okay, this is doable, and it's good to know that this is what we'll need to put in the elevator shaftway. So now I'm going to pivot a little bit and talk about some support scheme options. So because Walter P. Moore did both the structures as well as the enclosures, we were able to have a really honest chat with each other about, okay, how can we leverage the steel structure as well as the facade in order to basically balance how frequent these steel supports are, because they're only there to support the facade. They're not providing any performance to the structure itself. What can we do? So looking at the module and the structural the rhythm of the structure, we thought it would be either 42 feet, 21 feet, or 14 feet would be the frequency of how often the steel is going to basically go up this atrium. With that in our back pocket, we started looking at what ways in which glass can be put onto the space here. Like how can the glass span, basically how can the glass fill in between the steel pieces? So we really thought of three options: a patch and stick system, a traditional curtain wall, and a long glass span curtain wall. The first one, the patch and stick, is essentially sticks, verticals that are installed, and then the glass is installed on it with some localized patches that restrain the glass. So you can see in the image all the way to the left there, that's one built example in Brooklyn at City Point. It's a shopping mall, and that's the main entry space. So you can see in the nighttime view how clear it is. Like, you don't see any horizontals, like you only see black lines, and that's the silicone joint. That's the joint between the glass itself. So really high visibility, like A+++ points for transparency and minimal structure. And over here on the image to your right is a rendering, an image that we had put together to explain this concept to the architects and also our structural engineer colleagues. The tube that you see is what the structural engineers would be providing, and then the patch and then that vertical would be part of this patch and stick system. Now, to touch upon the traditional curtain wall system, a traditional curtain wall is essentially glass that is installed outside of the slabs. So that's why it's called a curtain. So much like a curtain that you have on a window, it flies past the slabs itself. That's how it gets its name. And so I have a couple images here of some really famous curtain wall projects. The bottom left-hand corner is one Waterline Square. It's being constructed. You can see all of the orange filter fabric, sort of OSHA fall protection items, and you can see how the glass is getting installed. It's basically being stacked all the way around. So similarly to the image all the way on the right here, you can see how the panel is getting just nudged next to its neighbor on top of the floor below. And that's how it gets installed. So these images all quite apply to as well to the long span curtain wall. So the option there was that we were thinking, well, maybe you could optimize it. You can compromise on slightly longer glass and more frequent steel elements, but then you could have more glass. So you have one less horizontal element. And so the image there in the middle is an example of how that can be achieved. So with a longer glass, even if you have more horizontals at other locations, it still looks really glossy and really high transparency. So to orient ourselves around the building, we talked about the metal panel, and now we look at the east elevation. The options I've just talked us through are those options that apply to this specific facade type. So you can see in the neutral position that patch and stick system and how it looks in exploded axon. You can see the patches coming in and out. And then here for the neutral position, you can see how the steel structure is every other horizontal element. And then you can see here the third option still has the same frame as the second option, but the glass is taller. So in a way, you see less of the structure itself behind it. So juggling all of this was, there's some pros, there's some cons to each of them. And so a lot of it was about how do you have that conversation and then make a good decision to go forward for the project. So going to go here. So to summarize here, we've got this patch and stick system all the way to the left, and you can see those patches. Those are the little elements that basically hold the glass back either for wind load or dead load. And here, the middle one is a traditional curtain wall type that's got the glass that gets installed into a frame, and then similar to the image we saw, it gets slipped into all its neighbors and friends. And then there's an image all the way to the right here that has the same type of construction, but there's more frequent steel. So you can see how the option all the way to the left has maximum glass and maximum spans between the steel, but it's also unusual. It's not as used as frequently and as often as the other two systems. The middle one, you have slightly less space between the steel elements, but you have an additional horizontal for the glass itself. And then the third most one, you have steel at every single horizontal. So you have a thicker sight line, but your glass is slightly taller. So in a way, it's like, well, the last two are really more traditional. People know how to use them. From a cost perspective, it's also less expensive. Which of these three makes the most sense? So which approach do I like the most? Personally, I really like the leftmost one. But before I break it to you about what we did for the project, I thought I would check in. Annie, do we have any
We
questions?
do. So the first question is, what is your favorite material to work with?
Oh, um, wow. I think it would be a toss-up, actually. Um, I really like glass to because of its transparency and the technology that's evolved in the last 5 years about what can be done with glass. So not only just glass that can be cast and formed in different ways and still be a facade performing exterior material, which is really cool. Um, it can also be now is used now because of the advanced technology, it's a lot more accessible. So atriums and entry spaces can have this really lovely glass element, glass moment that really wasn't accessible maybe 5, even 10 years ago. But the second material that I really like to use is actually stone. So stone is really hard to work with because it's nature's material and you can't really control it. But wow, it's really a showstopper when you work with a great quarry and there's a good story about how the stone is sourced. And if it's historical stone that's sourced near the project, that's like triple points because there's a lot of history of North America construction using stone, and that in a way it's kind of bringing back what we know from stone for all these decades and now giving it a new life and modernizing the look and the material.
So how do you keep informed about all these different technologies and materials as they come to the market?
I read a lot. I have to read a lot. Um, I know they some folks get their information from podcasts or from videos. I too do that, but I find reading to be the most powerful. And also working on projects from different places using different materials. I think there's nothing quite like realizing that you have a project and there's a question you don't know the answer to. It's very exciting, and that makes no 2 days the same.
And then how long did you work on this project that you're sharing with the group for?
2.5 years,
Okay, a long time.
indeed.
Oh, all right. Let's hear more about it.
Sure. So, drum roll. The approach that we ended up choosing was the rightmost one. So that's the one that has a slightly taller glass, and you have steel elements every 14 feet ish. So you can see on the right hand side that steel going up, that white paint is called intumescent paint. So it's fireproofing for the steel itself, so that when there's a fire, the steel is safe essentially. Now you can see on the image on the left how it looks with the glass on. And I think we can all agree that it is plenty glossy. I myself have not gotten a chance to go see the project at nighttime, but it's going to look really cool, I think, once it's starting to work because that glass is actually quite clear and it's going to look really cool when the elevators are flying around in there. And so one of my favorite things is to compare the architectural image versus what is built. It's just one of those things of saying not so much like, oh, did we do a good job? But it's more important to be like, were my expectations reasonable and did we achieve a cool looking building? And for us, I would say yes. So in the image on the left, that's an architectural imagination, it's a rendering of how the glazing is going to interface with the concrete with the articulated panel, that angled panel. And you can see the image over here to the right, the elements that are going up and down, the square looking ones, those are called trusses, and that's part of the crane that was installing the panel. But you can see the materials come together and the clarity of the material as well for the glass and the shimmering effect of the metal panel. And I would say we did a pretty good job. I'm really very excited to see the project complete, and it's going to open, I believe, fall of this year. So it's just been a really cool wild ride. This is my first project in Atlanta and I'm really excited for more.
Okay, we'll give everybody a couple minutes to type in any additional questions. Kat, this was really informative presentation. Thank you for sharing your story. And We have been trying to do these sessions every month. However, next month, August, we have a lot of our people are taking vacations. So we are going to take a summer break, and we will have our next session in September. So if there aren't any other questions, then we will see you all in September, and thank you for joining us.